Oh, you're with me. Ha! I forgot. Let's look at the slides again. All right. So here we are. This is kind of not a great derivation because you really need integral calculus to do this derivation. But by the way, voltage and stuff, that is a scalar quantity. So when you're actually studying electricity and magnetism, you like working voltage problems. You know why? Because it's all scalars. You don't have to deal with vectors. And when you start doing calculus with vectors, it gets hard. I mean, the algebra that we do with vectors is kind of tricky enough, but you start throwing in directions and stuff like, man, this is hard. I'm trying one of those Keurig things out of the vending machine. That was god awful. For what, $1 more, I could have walked across the street, got 3 times as much coffee, and it would have tasted good. Anyway, damn, what a ripoff that was. All right, but I'll try it again. Sorry, wasting your time. All right, so here's the potential of a point charge that we saw. All right, now one of the things that we like to do, just to make sure that we understand this, using a zero reference, in other words, way out at infinity. All right, we're going to place where r is out at infinity. We're going to place this charge right here at 1.2 meters away from a potential line, a potential that is positive 300 volts. What is determine the amount by which a point charge alters the electric potential at a spot 1.2 meters away, when the charge is positive or when the charge is negative. Okay, so it's a 300 volt. It's a 300 volt right here. Okay, and we are going to see how much this thing changes this. What are they doing? I don't even know what they're freaking asking here. I hate it when they do this shit to me. All right, sorry. It's positive. Oh, I didn't know those came out to be positive. Oh, I guess you do when you multiply by k. All right. I thought this was a given, and we were going to find when we put this charge, we were going to add it to that. I'm sorry. So it turned out to be, I was making it harder than it was. And pardon my French when I do this. I shouldn't do that. That's not very nice. All right. It's unprofessional. It's unprofessional. All right. Here we go. Now, the electric potential. Let's find the electric potential at point A, and let's find the electric potential at point B. Remember. Notice, real quick, notice this Q does not have absolute values around it. Okay? This Q does not have absolute values around it. All right? So keep that in mind. We're going to notice they did the positive on this one, and for this one they would have done the negative. They'd have put the negative charge in there. All right? So now, what do you think the potential is at B? If this is positive times 8 times 10 to the negative 9 coulombs, and this is negative 8 times 10 to the negative 9 coulombs. If we add those two together, what do we get? 0, regardless of because they're equidistant apart. What is he saying? Some of you are going, what? Say what? No, look. I'm just saying, Mother Nature loves symmetry. This is the positive 8.0 times 10 to the negative 9 coulombs. We come out here, and this is negative 8.0 times 10 to the negative 9 coulombs. All right, and we take a point right in the middle. And this is R, and this is R. I can just do this algebraically. I can just do K times, or conceptually, 10 to the negative 9 coulombs over R plus K times negative 8.0 times 10 to the negative 9 coulombs over R. I can factor out my K over R and get 8.0 times 10 to the negative 9 coulombs. Some of you are going, yeah, we get it. Minus 8.0 times 10 to the negative 9 coulombs. But I'm just hammering it home. That goes to 0. So right here in the middle, it's 0. But let's figure it out where it's at 0.2. This is 0.2, and this distance is 0.6 meters. And this is negative 8.0 times 10 to the negative 19 coulombs. And this is 8.0 times 10 to the negative 9, not 19, 9 coulombs. That one's positive, that one's negative. We're going to find it right here. First of all, you think it's going to be positive or negative? Because we're going to get V1 is equal to K over 8.0 times 10 to the negative 9 coulombs over 0.2. V2 is equal to K over negative 8.0 times 10 to the negative 9 over 0.6 meters. Magnitude-wise, which number is bigger? This one, because we're dividing by a smaller number. We're dividing by a bigger number here. So basically, we've got K times 8.09 times 10 to the negative 9 divided by 1 over 0.2 minus 1 over 0.6, or whatever that comes out to be. Why does this iTunes keep coming on, driving me nuts? I hate it. I hate iTunes anyway. iTunes. Yeah, I got your iTunes right here, dog. Anyway. So that's what we just did for A. Here's for A. Comes out to be positive 240 volts, just like I thought, and 0 right there in the middle. All right. Where's this 0? That's a nice like in-class question. Be prepared to kind of do this one in class. Got a positive 2. Where would this thing be 0? Where could it possibly be 0? The positive charge is 0.2 and the negative is negative 0.2. This is conceptual. On the line that passes through the charges, how many places are there at which the potential is going to be 0? Well, since this is twice as big, this is tricky. This is tricky because I know right here this positive charge will dominate this one. The negative charge will kind of dominate this one, and it's going to be divided. Oh, it looks like this is 2 segments. Looks like it might be a P2. Whereas P3 is being pulled, the distance away from Q is so small compared to this one. I think that'll be negative. I think it's a P2. That's what I think. And since they don't give the answer, that's what I'm going with. Actually, we can find the answer in the Wiley process. And I might look at, so that's conceptual example 7. I'll look that up to make sure. All right, here's what I was showing you before. Equal potential surfaces. Notice, if I'm going from A to B to C, those surfaces all stay. The net work, electric work done to move me from here to here, nothing. There is no net work. However, if I'm a positive charge and I go from A to D, that's the same as going from B to C and C to D. It doesn't matter. That's the nice thing about it. We don't have to calculate things that are cattywampus. It's wonderful. Okay. But I know as I'm going from D, that's going to require, if it's a negative charge, it'll do positive work as it goes from this lower potential to a higher potential because that's where it wants to go. If it's a positive charge out here at B and I'm going this way to D, then it's going to be doing negative work because we're going to be working against it. Like we have to do positive. We're going to be increasing its electric potential. Okay. Okay, so this is the higher potential. This is lower potential. these electric field lines coming off this charge, notice they're at 90-degree angles. Here again. And then right here, this potential line here is 0. But notice the electric field lines, the electric field between the two is not 0. The electric potential is 0, right here smack dab in the middle. But the electric field is definitely not 0. Okay? All right, and we'll talk about this one in the next video.